So thank you, Christina, again. I know that we are many hours apart, so it's very early for you up there. So thank you so much for accepting my invitation. So for
No
those who,
problem. This is my second meeting already, so.
oh my God, so you have breakfast already. So for those who doesn't know, Kristina Lerman is a principal scientist at the University of Southern California, in Information Science Institute. She also holds a joint appointment at the USC Computer Science Department. She's a research professor there. Her formation is in physics, and she used network analysis and social media analysis to study uh, computational social science. Her recent works on modeling and understanding cognitive bias have been featured not only on the academics, but has been featured on the general public and featured on Washington Post, Wall Street Journal, and many others. So it's my pleasure today to 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 hear more from Kristina. Thank you, Kristina. So
Thank
I'll
you,
stop sharing
Diego.
my screen and go ahead.
Okay. So, okay.
And by the way,
Stop screen share. Okay, that's fine. There you go.
we will, for those who didn't hear, we are recording this and we'll put this record after on YouTube.
So let me just a little bit, I'm going to still trying to get used to Zoom thing. So I'm going to put,
You can put your questions on the chat.
okay. And I like to point things around. So let's turn a laser point around. Okay. And you're going to handle the waiting room, right?
Sure,
So
sure.
things are, it's a
Yeah.
little bit distracting to have things pop
Yeah.
up. But anyway, so thank you, Diego, for a nice introduction. I'm really excited to share results of my kind of latest work. Things have been consuming my attention in recent days. All right, so I'm right now, as Diego mentioned, I was trained as a physicist. Now I like to call myself computational social scientist because I'm actually really fascinated with social science and trying to learn, see what we can learn about human behavior from data. So suppose you have a question, you want to, like as any social scientist does, you want to find out, is higher income associated with greater happiness? Does making more money make people happy? Well, as a scientist, what you're going to do is go look for data that has this question. This is actually what we did. This data represents results of study we did using tweets, where we collected tweets from around Los Angeles County, and we measured the sentiment or happiness, expressed in those tweets. And then we had for each tweet, we localized them to see where within Los Angeles County it was coming from, and then linked it to the socioeconomic characteristics of the individual neighborhoods. So each point is a neighborhood, and the y-axis shows how happy the neighborhood is, and the x-axis shows the income, log of the income of the neighborhood. All right, so, and actually this is fairly typical of social data you receive. Whenever you look with social data, what you get is a cloud. There's lots of different cloud of points, but no fear, social scientists have invented tools, techniques to work with data clouds. For example, we can do just linear regression. And this linear regression would say, okay, I try to predict the Y outcome, happiness, as a function of X, which is income. And lo and behold, we have a positive relationship. You have a positive regression coefficient. So there's, the richer neighborhoods have higher or more positive tweets coming from them. And look, p-value is highly, highly significant. So this is a really good relationship, and then you'll be happy and write a paper to report results. But as often happens in social data, there are confounders that might mislead you and hide the true relationships. Here I took the same points, and then instead, I colored these points right now by the education level within each neighborhood. Basically, the color represents the fraction of people, percentage of people who have college education or above. And then the story is not so clear anymore. When you stratify or when you disaggregate, I'm going to use this word a lot in my talk, disaggregation or stratification. When you disaggregate data by education level, you might see now like you actually lose relationship between happiness and income within each class. For example, if you look at the yellow dots, it looks like income does not actually have much impact on happiness. Or within the blue dots, which are low education, also relationship looks quite flat. So why does a positive relationship seen? Because people who are more educated, they earn more money and they tend to be happier, or at least post happier tweets. So this is not just a problem with this data. This appears every single time. This is what we call the hidden confounders introduce bias in data, and they pose threats to the validity of models. And when I first started giving talks about this, people said, well, it doesn't really matter. And well, if you still learn some sort of predictive relationship, does it really matter whether there are confounders? And I like to claim, I will hopefully convince you that it really does matter. These hidden confounders or biases in data, they present multiple threats to validity of models. They're threats to prediction. They lead to non-generalizable, non-reproducible data. If I now go and I measure happiness in England, for example, I might actually get completely different relationship between happiness and income because it's a different population. So the models that you learn from this data will not generalize, and they will lead to poor performance in held out data, new data sets. These biases also offer threats to validity of explanations. Social scientists trying to get to some mechanistic explanations about human behavior, to causal models of behavior, and these types of biases might mislead it. Actually, this is known as ecological fallacy in social science research, when you're trying to make inferences about individual behavior from the population trends, and it often doesn't work. And these are precisely these types of reasons I'm going to be talking about are why it doesn't work. And if you don't learn good models or mechanisms from the data, you're trying to learn mechanisms about human behavior from the data. If you don't learn correct ones, then you will not know how to, as a policymaker, how you can intervene to improve this. For example, if I wanted to, there was a correlation, for example, between education, like health, and number of books. For example, people who live in kids who are learned in household that have many books in them actually end up being better off. They're healthier, for example, living longer life. So there was actually a program, I've forgotten which state in the United States, in Georgia or somewhere in the South, where the governor actually said, oh, well, there's a correlation. So each newborn actually was born in the hospital was sent home with like 2 or 3 books, to start off a library that will improve their health in the long term. Well, this was just false, because there was a hidden confounder, which was education level of the parents. So parents who were better educated, they had more books in their house, and also raised kids who had healthier diets and lifestyles, who lived longer and were healthier. So again, there's multitude of stories like this where faulty relationships lead to bad causal policies and interventions. And an additional final threat to validity of models is the impact on fairness. Models that are learned from biased data may entrench or amplify existing discriminations. And hopefully I will also have time to talk about some of the fairness research we're doing right now. Hold on. Okay, so this previous slide also gave an outline of my talk with the messages I'm trying to convey. And I will give you many examples of the types of paradoxes that arise. I will show you the work that we're trying to do to try to manage these confounders and the biased data. And then I will also leave some time to talk about algorithmic fairness. It's a really fascinating subject that is now attracting increasing attention. All right, so there's a number, many different types of paradoxes, sources of bias in data. This, I'm just showing you 4 because this is the 4 that we have actually done work on, but there's numerous other ones, and it would be interesting someday soon, hopefully, that to try to systematically enumerate the types of paradoxes. So you'll hear a lot about Simpson's paradox because it has been the focus of my research for several years. And if you haven't heard about it, and I'll illustrate later, it's basically, it's a very common type of paradox where you see, like what I was showing you with the happiness data, where you observe a trend in the population behavior, but the trend disappears, and actually in some cases even reverses when you disaggregate or stratify the population into individual groups, subgroups. This is also related to sampling bias, when you don't sample groups equally from the population. But there's also other types of really fascinating biases that often arise even in your work and research. I'll talk about survivor bias in social media data. And that arises because your sample might actually change as a function of the variable that you're using to measure the behavior. And this is aggregation bias is right now a catch-all term. We're still trying to disentangle things, but there's different types of aggregation bias where you might be observing one trend. Suppose if you get data from one spatial unit or from one period in time on temporal time window, but if you look over, aggregate over different spatial areas or different multiple time windows, you will actually get a different trend. So this brings into differences between longitudinal analysis, where you're following a cohort over time, you get one trend, and cross-sectional analysis, where you take different multiple cohorts of different ages and put them together to measure the trends. And you also can get very different behaviors in these 2 cases. Okay, so what's Simpson's paradox? This was, I love Simpson's paradox so much. I'm trying to call myself, Simpson's evangelist, to promote the understanding of Simpson's paradox, because it's actually everywhere, and in all your data sets as well. Okay, what is the Simpson's paradox? Actually, I should say the data set I'm showing you here, the gray points, that it's a synthetic data just to illustrate it, but trust me, it's everywhere as well. So if you look at the gray points, it's showing some relationship between an outcome, which is the y-axis outcome, and some independent variable x1. So usually, that's what in your work you're trying to measure. What is the relationship between the outcome and some feature? So if you look at this data, gray points, ignore the lines for a moment. So if you just look at the data, squint your eyes, you see a cloud of points, as I was mentioning. And the general tendency of this cloud of points is positive. This is the red line. This is what linear regression would give you. There's overall tendency that as you increase the independent value of the feature x1, your response or outcome will also increase. But unbeknownst to you, there's some hidden groups. The data actually contains some groups. Maybe this is, body mass index, y, and x is how much pasta you're eating. And even though it looks like there's, the more pasta you eat, the more higher body mass indexes, but there are some athletes. You have athletes who have, who have different types of relationship than older people, who in this group could represent older people, and this group could represent very fit athletes, and within each group you might have different relationship between body mass index and pasta consumption. So if you knew about these groups and could separate the data, you'll get these green lines that have the trend within each subgroup. So Simpson's paradox says that the trend appears in different subgroups of data, but can disappear or reverse when these subgroups are combined in the population level. There's, as I said, there's multiple examples of this. One of my favorites, because it actually links to the fairness aspects later on that I'm going to mention, is this title in my slide is being blocked out, but probably not in yours. So the title of this is a paper from Science from 1975 that's talking about sex bias, sex discrimination case that was brought against UC Berkeley, in which they said that the plaintiffs claimed that Berkeley discriminated against women because if you look at the data, you look at how many men and how many female applicants were admitted, you see there's actually systematically fewer women were being admitted. So only 35% of female applicants were admitted for graduate studies at Berkeley, but 43% of male applicants were. So this was portrayed as evidence of bias against women. But turns out it's a Simpson's paradox. You know, this is where it was influential paper. If you take the same data as was produced these numbers, and now you disaggregate the data by department, and you plot the percent of candidates of each gender that were admitted within each department, you actually get a different story. So this plot is showing within department, fraction of men and women admitted in 6 different departments. So what do you see? Actually, what do you notice here? Well, lo and behold, look at this. Within each department, actually, women, there was even some preference for women. And in others, they're more or less the same. So there was actually no discrimination against women. And if anything, there was some preference towards women if you disaggregate data across departments. So what's going on? Why does the paradox arise? Is there bias or is there not bias? Well, what's going on? Well, like, what do you think the differences are this department? What do you think, if I were giving a class, I would ask people to call out, what they think, what you see from here, this plot, is that some departments are very easy to get into. They admit 60 to 80% of their applicants. Some departments are very hard to get into. They only admit, they'll admit less than 10% of their applicants. Which departments do you think these are? Well, turns out these are the hard sciences. This is the engineering and sciences departments. Fewer people apply, and of those people who apply, many more fractions are admitted. And these departments are like humanities and English language departments. They're very difficult for applicants of either gender to get into. And it happens that many women apply to these departments that are hard for anybody to get into. And fewer women apply to these science departments, which are easy for any applicants of any gender to get into. And so after you average over all the departments, you get these trends. This is like the horizontal lines represent the average fraction of women and average fraction of men that they're applying to. So again, more women apply to hard departments and fewer women apply to easy to get into departments. So is there discrimination or not? Well, yes. I mean, even though discrimination doesn't arise to at the level of decisions to admit applicants to graduate schools, the discrimination is in a pattern of interactions that women have had that channels them to apply to departments that are harder for both genders to get into. Okay, so that was Simpson's paradox. Simpson's paradox is, and actually, by the way, if any of you have questions, I'm happy for you to interrupt me and ask questions along the way.
We have one question, Kristina.
Okay.
So Rawson asked, how do you select the factors such as education, income to show happiness?
Yes, that I will show you later. That's the crux of the issues, of course. Yes. So hold on to that question and till later in talk. Anybody else? Great. So now hopefully you won't hear the gardener. Gardener showed up. The dog is barking, but hopefully you didn't hear any of that.
Hello.
Yes?
May I ask another one question about previous diagram? Yes. How it possible if totally, you said that it's the same data, but when we look at the first, we can see that totally woman less than men. But when we move
on the right,
second, yes, in general, we can see that the woman much more than.
Yep. So because you're doing this average, so this 43, this is right here, and this is 35 is this red line. So this is going to be averaged by you multiply the rate times the number of people who apply here. For each department, you have to multiply the rate at which people get and times the number of people from each gender. You know, number of women who apply to here times the rate. Number of women apply to this department times the rate. So because so many more women, most of the women apply to this department number 6, and very few apply to department 1. That's why it's skewed.
Okay, thank you.
Okay. Yep. It's part. Thank you. Yes, those are all very worthy clarifying questions. All right, sampling bias. You know, this arises because you might, you know, next time you run a study once, you collected this from groups, you didn't know about the groups, subgroups existed, so you run the study second time, maybe you oversampled one of the groups. And unless you know that these groups exist in data, your linear regression might now come up with completely different conclusion. So sampling bias is somewhat related to Simpson's paradox, and you need to know about subgroups to handle it. Survivor bias, this is actually one of my favorite also examples. There's many other examples of it. It shows you that how easy it is to be misled. So this plot comes from a paper in 2011 by Romero. There's actually John Kleinberg, who's one of the leading computer scientists. He is also one of the authors in this paper. And what they were measuring is, you know, how likely are you to retweet, use a hashtag or retweet something. We talk about retweeting, retweeting topics, but here they were looking at hashtags. So how likely are you to use a hashtag, P, probability you use a hashtag, given X is the number of friends of your friends, the people you follow who tweeted the hashtag. So so you can see actually as more of your friends start using the hashtag, you're more likely to use the hashtag. But until a certain point, then it looks like you're less likely to use the hashtag when more of your friends use it, tweet it. So the whole paper was actually, they showed this plot, and then the rest of the paper is about where the peak occurs and how quickly it declines based on different categories, was the political, sport, entertainment, or sports, and so forth. Well, this is just a paradox. This is not real. This is just the artifact of these heterogeneities in data and different populations that exist. What happens, and this we did this, but we got the same. We did this actually for retweeting URLs to news stories, but it's the similar things. I'm sure if we used the same data as they got. But what happens is if you see what is the probability you retweet some post that your the friends shared, and but as a function of the number of friends who tweeted. So we would actually we got the same thing. Like as more friends tweet, actually probability goes up. But actually, and then turns around if you aggregate over the whole population would turn around and just go. But what's happening underneath? Actually, your population of Twitter users is highly heterogeneous. There are some people who have few friends. They only follow 5 people, 5 others, for example. So when they go to Twitter, those 5 people maybe posted, 10 messages in a day or something. So they have very short newsfeed to read. And they're highly likely to see anything that's posted in this, and they're highly likely to retweet it. So the probability to the more of their social feed, newsfeed fills up with this particular story, news story, the more likely they are to retweet it. But there's other Twitter users who follow many, they follow 5,000 other users. They have many friends. And so their 5,000 friends, post a lot of things. They have a very long social newsfeed. They see very many messages to get through. So the probability they will see any particular message is low, and they're less likely to increase it, to retweet it. So it still, goes up. The more of their friends talk about something, the more likely the user herself is to talk about it. It goes up, but much more slowly than for people who have few friends and have shorter feeds. And what happens when you try to produce a plot like this by aggregating data across all these different people who have few friends and who have many friends? Well, in the beginning, it will go up because everybody contributes. So your probability to retweet something will go up the more your friends tweet about it. But at some point, people who have few friends start dropping out of your sample that you're averaging over. And because they drop out, actually, this will decrease the overall response, and you'll get this kind of peak and decrease, but only because your population is different, because you cannot have 40 friends tweeting about something if you only follow 10 people, right? Hopefully that's clear. So this is called like survivor bias, where as your population changes, the population's properties, behavior might change because some people drop out of that. And again, this is quite common. All right, another thing, actually, there's different types of aggregation bias. There's temporal aggregation bias, spatial aggregation bias. I wanted to show you an example of spatial aggregation bias, which is probably will be very near and dear to people's hearts. It's about COVID infections. And actually, this was a paper study analysis we did back in April. We're actually updating it with more recent results. But we looked at data about counties. Counties, basically, you probably have similar concept in England, but there's United States is divided into 50 states. Within each state, there's counties. There's about 6,000 counties across the US, and data about COVID infections was being reported at the level of counties. So you can see here, this is showing within New York State, there's many counties in New York State, and this is showing how the number of COVID infections is growing over time in each county. And then you get actually the entire state population, you can see by just summing up all the counties, and you get the number of how the number of infections across the state is growing in time. And one of the parameters that people measure is the growth rate of COVID infections. How quickly is it spreading? So you can actually fit each of these lines. You can actually fit it to estimate the exponent, the growth rate of the infection within each county. And this is actually, this plot is showing distribution of growth rates across counties in the US, and this is April data set. And then most people actually look at the level of states. But again, you just sum up all the counties, you get the growth rate in each state, and you can do the same thing, estimate the growth rate of this curve. And you look at actually these state growth rates are systematically higher than the growth rate of counties. So infections appear to grow, within states they grow faster when this data is aggregated across counties. So, okay, so within each counties, actually they grow slower than when the same data is aggregated to get states, and slower still when the same data is aggregated across the entire country to get the growth rate of COVID infections for the population as a whole. Again, this comes because the counties that have the highest infection rates, like the New York City, is actually, New York City, we combined actually, New York City is one of the most populous counties within New York State, and happened to be the one where infection appeared earliest and grew fastest. So it's actually skewing the growth rate for the state. But the same thing that Simpson's paradox and the Berkeley admissions, kind of the same effect is coming through. Okay, aggregation bias. All right. And also this is showing. This is also if you drill down within. This is the black line is for Los Angeles County, and we had data for neighborhoods. Individual neighborhoods within Los Angeles County, you get the same story at this different spatial scale. It looks like in the county as a whole, black line, it looks like COVID is spreading faster than it is within individual neighborhoods, which is this curve is representing distribution of growth rates of the COVID infections within individual neighborhoods of LA County. Actually, I have more to talk about COVID, but maybe not in this talk, in another talk. All right, so what can we do? How can we, this was the question earlier, how do we figure out what these confounders are and how they affect the data? So we've done, I'm going to talk both of how you handle observed confounders and also latent confounders. So this work, actually we have the most papers about it. There's even code exists for this, so you're welcome to try it on your own data. So we can actually, we showed in this series of papers that we can automatically identify when Simpson's paradox confounds analysis of our data sets. So this method I'm going to talk about, it systematically disaggregates the data into more homogeneous subgroups and looks for functional differences or looks for trends within these subgroups and pooled population level data. And the method is actually really simple. It has like 3 steps. First, you look, you given a table of data, you have some outcome Y, and you have a number of explanatory variables X. Could be, for example, you have 100 different explanatory variables. First, for the outcome, you look for a trend with respect to each in turn. You choose one of the explanatory variables or features, and you look for a trend within that variable. As a second step, you choose one other variable in your data. You call it XC. You choose the next variable, and you disaggregate. You essentially bin the data by this variable XC. So there's some magic or some things that are going on, but you can look at the papers to read this. But essentially, what this simply does is taking with respect to this variable XC, it basically bins the data so as to optimize R² within each bin, how well the bins separate the data into different classes. And then within each bin, you measure the trends again. You measure the trend of the outcome Y with respect to explanatory variable XP, but within each bin separately. And then the code looks for when the trend systematically shifts. And we apply this method. Well, actually, it's a little bit backwards. We came up with this method after we discovered lots of Simpson's paradoxes, but we then applied it, and it actually to validate the method that it really does work to discover these types of paradoxes. And it actually, this method does lead to some new insights into this into human behavior. So a number of so we looked at a number of data sets, and we're consistently finding that within each data set, whatever performance we are measuring, and I'll show you some examples of it, that relationship completely reverses when we disaggregate by how long people have been working online. So this is an example of, I'll show you evidence for cognitive depletion. Basically, the more time people spend online, the worse they perform. And this is true for the data set we looked at Facebook, whether they're, how people are browsing Facebook, the message they're posting on Reddit, the quality of the comments they write on Stack Overflow, even the accuracy of the problems that they're solving on Khan Academy. We're observing very consistent behaviors that indicate these types of cognitive depletion is going on. Fatigue affects the quality of their performance. So for example, in Stack Overflow, which we studied, this is part of it's a question answering. I'm sure many of you are familiar with this. This is a question answering site for programming questions. So you're stuck in some, doing some programming task. You go to Stack Overflow, you ask a question, and then other people answer the question for you. And if each person an asker can ask a question, multiple people can reply to a question, and then the asker goes back and accepts one of the answers as a good answer. So you'll accept and say, okay, this answer answered my question. So we can actually measure the acceptance probability for each time when people write answers. What is the likelihood that the answer will be accepted as a good answer, given it's the first answer the right, second, third, fourth, 10th, and so forth. This is we can look at each person each answer and see how many answers they've written and see, do they write better answers? Are their early answers better or the later answers are better? So if you do this across the entire population of questions and answers, so it looks like, the answers that are written later, they're more likely to get accepted, to get this positive trend. So it looks like later answers are better, up to like 38% of answers that are written later are likely to be accepted versus like about roughly a third of the answers written earlier. But this is an example, well, maybe survivor bias, I guess, rather than Simpson's paradox. Because if we take the same data and now we disaggregate it or stratify, separate the data based on session length, how long do people work on this? When you go to Stack Overflow, you sit down on your computer, you start answering questions, then you take a break, maybe you come back 2 months later, you start answering questions again. So some people answer only one question and then they leave. Some people answer 5 questions before they leave or so. But if you now compare, look at the probability that answer is accepted, but you compare people within each group based on how long they stay online, to answer questions, you get a completely different trend. So here, like people who answer 5 questions, their first answer is better than the second answer, which is better than the fifth answer, meaning like the first answers are more likely to get accepted as good answers rather than later answers. I saw a question or something pop up. Maybe you can read it. Yeah. If there was a question.
I don't see anything.
Okay.
So as a result, for example, my fifth question will be better than first. It means like, because I'm already in this discussion a long time, so I can understand some. And I can create some better questions. So
but this is like, it's not. So if looking at people who write 5 answers before they go and they come back, they might have another session, but looking within each session, the first answer is going to be better, more likely to be accepted than the last answer. And why this is a paradox is happening, because the vast majority, like 90% of people only write 1 answer before they go. So these people who write 1 answer tend to be people who just joined Stack Overflow. They maybe they're newbies and they might write 1 answer and go away. Their answer is not very good, high quality. But these people, there's fewer people who have write 5 answers, but they're much more committed. They're maybe veterans. They're much more dedicated to Stack Overflow. So overall, their answers are better. But even though their answers are better, within the session, they still manifest this kind of cognitive fatigue, or depletion, where their quality of their work decreases over time. But the paradox
labeled this author of answers like an expert. I saw this. So I saw
That's
this label that it's an expert or some junior answer.
That's right. These are kind of junior people, more likely to be junior people. These are more likely to be more experts. So overall, it's better, but they still have depletion.
And I'm surprised with your first diagram, because it's this situation which I met just yesterday. I saw 2 answers and I selected old.
You select the older one.
But I don't know why I selected old. I'm just looking both of them and I selected old. Now I understand.
Well, yeah, that is also, we have another study. I mean, we can look at the, wait, who let it, sorry.
Yeah, thank you. Now it's clear for me. Why?
And what happens is actually because most of that is here, so that's why it weighs down. But when you start looking at how good are answers that are written second, well, people who only write 1 answer drop out of the population. So, could you close the door, please? So that's why it actually, so they dropped out. That's why the response goes up. And then when you look at answers in third position, nobody who wrote 1 or 2 answers contributes. So the average of this, there's higher, so it gets skewed higher and higher. And that's why you get this overall positive trend. All right. Oh,
Thank you.
Yeah, thank you. I'm going to skip through this. I want to spend actually, we can do this for latent confounders when you don't know what the classes are. But I want to make sure that I handle, also do talk about biased data. So I want to, so I apologize, I skipped some slides, but I want to talk about this is really interesting and really relevant, Okay, so it's about algorithmic fairness. So what does it mean to be fair? So intuitively, I mean, there's still lots of discussion within the community, but intuitively, it means that your private attributes, whether your like race, gender, we can have many other attributes, ethnicity, sexual orientation, whatever, but your private attributes should not affect how you're treated by the algorithm. Whether this algorithm is doing, your credit score, how much money you should get from the bank, or whether you should get into some college or graduate school, or so especially, when those attributes are not relevant to the decision that's being made by the algorithm, that everybody can probably agree that your private attributes should not really affect those decisions. But there's still lots of discussion in the community, in society in general, what does it mean to be fair? And it's really also that, whatever metrics you come up to measure fairness, they're often incompatible with each other. This question actually exploded in a scene. People have been thinking about it for a long time, but in 2016, ProPublica came out with a study that was talking about automated risk assessment tool, and then like a whole new field was born in 2016. So ProPublica looked at this software tool that was a result of social science and criminologists were trying to make it easier for judges to evaluate whether or not a defendant was going to commit a crime in the future. So based on studies that social scientists did, they came up with this kind of, I think it's basically a regression model in the end. But and then the judge or the software tool will feed in for each defendant that the judge was considering. It would take those features of the defendant, the characteristics of the defendant, and feed it into the algorithm and come up with a risk score. So either it's a low risk, like this, I mean, the person, there's, in the next 2 years, the person will have 30% chance of committing a crime. Other people who were given a risk score of 3, of those 30% committed crime. Or it will come up with a high risk score 8. So meaning like of all the people who who were given a risk score of 8, 80% of them committed crimes within the next 2 years or so. So this is what the algorithm was doing, COMPAS algorithm was doing, and ProPublica analyzed the algorithm because they had the benefit of hindsight. So they said, okay, let us take the data from this county in Florida where this tool was being used by judges to make their decisions, because then the judge will take this risk score and say, okay, oh, this person should be released, or this person has to go do some community service, or this person has to go into some interventions. So the judges were actually using these scores to make decisions about the fate of the defendants. So ProPublica took the data. They had they knew all the people within this Broward County who had been, where the tool was used, who had the risk scores. And they said actually in 2016, 2 years later, how many of those people committed a crime? So they could construct this so-called confusion matrix. They can see what the COMPAS tool did, will say, will this person commit a crime or not commit a crime? And what actually happened, they did commit a crime or they did not commit a crime. So these people here, there's a false positives. They're said, the tool says they will commit the crime, but they actually do not, the reform. And these are false negatives, where the algorithm says they will not commit the crime, but actually do. And what ProPublica showed that these were greatly asymmetries with this where the people were of each race were falling. So among the people who do commit another crime, this is the incorrigibles. I'm showing you here what the distribution of risk scores for each group, the blacks versus the whites. And you see actually the white defendants who do commit crimes, they get systematically lower scores than black defendants who do not commit crimes. And it flips when you look at people who never commit another crime, who the reformed pacifists that do not recidivate. And you can see actually the blacks defendants are who never commit the crime are given higher scores than the white defendants who never commit the crime. So there's this asymmetry exists, right? So when this came out, actually, COMPAS, the makers of this tool, they got all upset. It's like, oh, but we carefully calibrated the algorithm. They're careful. This is showing so-called calibration curves. They carefully calibrated the algorithm so that, for example, if algorithm tool gives a risk score of 4, then 40% of both blacks and whites, 40% of whites end up committing a crime. And if the algorithm gives somebody risk score 8, then 80% of defendants, both black and white, commit a crime. So they actually said our algorithm is carefully racially calibrated not to discriminate. And yet we do have this asymmetry in the effects. So what's going on? Well, it turns out it was a paper by Kleinberg, Molnith, and Ragavan that these are two fairness conditions, calibration and balance between classes. And they cannot be simultaneously satisfied, except for some trivial cases where there's no discrimination. For example, you have equal base rates of people committing crimes, or you have perfect, oracle that does perfect prediction. In other cases, you need to trade off one versus another, which is showing you how tricky the algorithmic fairness is. And another one actually is accuracy. So how well can you can use this risk scores to predict whether somebody will commit a crime, and 2 years later you can see how accurately they do across. And then you can actually say algorithm will make mistakes or not make mistakes. You can actually change the fairness for the algorithm to be more fair, and you can say, well, how accurate will be. And you can also show that improving fairness, reducing the mistakes the algorithm making on different within blacks or white populations will actually reduce its accuracy. So this is another trade-off in the fairness. So I wanted to show you a very simple way where you can actually construct some, improve the fairness of algorithmic predictions that will try to minimize the trade-offs that you have to make between these conditions that I was doing. And this is actually a very, very, very simple idea that I actually love. So suppose you're given a table of data, you have some outcome, you have some features, and you're trying to make algorithmic predictions. And then that are accurate, but also fair, because one of the features, let's call it XP, one of the features that you're given is actually some sensitive feature, like race, for example. Then you want to make predictions that will be kind of not depend too much on this feature. So what do we do? This is a very simple idea. You take this XP, this feature, sensitive feature like race, maybe gender, maybe age, and you create a space that's orthogonal, null space that's orthogonal to this sensitive feature. And then you project all remaining features, you project into this space. So the remaining features are guaranteed not to be linearly uncorrelated with this sensitive feature. And then you build models using these projected features to predict the outcomes. And actually, to add more interest, to make more interesting, we add parameter lambda that controls how much we use, whether we use how much of the original feature versus how much of the projected feature. We can come up with a linear combination of these features, and then we can dial the fairness parameter lambda to weigh more like the fair projected feature or to a original feature. Okay, and then, but the nice thing about this, then we can use these projected features. We can use it in any number of prediction models to come up with predictions that are more fair. We're showing. So in kind of in 1 minute, so I'm showing you actually here. We can look at how well it does. How does it change the accuracy? So using COMPAS data again, we compare different algorithms, and here what I'm showing in the y-axis is the correlation between predicted outcome and the sensitive feature. So the more information you predict, your predicted outcome gives about the feature, the less fair it is. So so you want it to be actually correlation to be 0, meaning that your prediction does not reveal anything about the sensitive feature. And what the x-axis is showing accuracy, how well are your predictions, how well your predictions are doing. So you see this kind of overall behavior that there's a trade-offs. The more fair your algorithm becomes, the more you pushing you down the correlation with the sensitive feature, the worse the accuracy becomes. But algorithms using, so these plots are showing different types of models that use our fair projected features. They're actually able to achieve much higher accuracy than other methods, much higher accuracy at lower correlation, like more fairness. And here actually, this is one trade-off between fairness and accuracy, but here also trade-offs between balance and calibration error. So here, balance, I'm looking actually, sorry, like looking at this, for example, for the whites, yellow bars, what is the average score? And for the blacks, what is the average score? And I'm looking at the difference, the difference in the means between these two populations. So this is what the y-axis is, just difference between the means of the two classes, like whites and blacks, for example, in COMPAS. And this is showing calibration error, like kind of the difference between those the two curves given the. So again, you see the kind of trade-offs is you try to decrease calibration error going left, you increase balance, kind of basically there's more difference between the two classes, difference in the mistakes that the algorithms making between the two classes. But again, this is actually these two curves showing balance for our balance calibration error trade-offs for our algorithms. It's actually better than other algorithms in the state of the art we compared it to. So showing that you can actually do better with these fair projected features that are guaranteed to be linearly correlated. And we have some paper for more details. All right, I did want to leave some time, a little bit of time for questions. So this was the race through the talk and showing you that actually you have to take into account confounders. There's different methods, but we're still exploring other methods to identify these confounders, especially if you don't observe the measures particular feature, but you have to infer them, these latent confounders from data, it becomes much more tricky, but you have to control for them if you want to make models that are fair and accurate and generalized to unseen classes data. And again, I'd like to thank my collaborators who were responsible for much of this work. Okay, and I'm open to questions now. Thank you.
Thank you, Kristina. I think we have one question here from Marcos. It would be nice to hear about the advantage of this method, the one you use on probably Stack Overflow, in comparison of just using multi-level modeling.
So yeah, multi-level or mixed effects models, actually this is, all right, so yes, this is similar, this is exactly multi-level modeling, but multi-level modeling or mixed effects modeling where you take some, there's some categorical feature, usually it depends on having some categorical feature, and then you assign all the data samples, observations to each different categorical features, and then you measure the trends within it, right? So that's, wait, hold on a second. This is automatic. Yeah, this is essentially what this is doing, but you're not, instead of giving categorical feature, you have to identify what the different categories are within the data. And so that's exactly what we're doing now. We're trying to write up this paper, and then I'm going to call it actually mixed effects modeling with like hidden classes. But so yes, this is exactly what this becomes. This is basically mixed effects modeling, multi-level modeling. But the tools that people have developed actually don't take into account that you actually have to disaggregate data, and there's a lot of thought that has to be put into how you disaggregate data appropriately.
George.
Any other?
Yeah, George, you can unmute and make a question.
Hi, thank you for your talk. It's quite interesting. I just had a couple of questions on the method you're actually showing right now. So I was wondering a bit about how the space partitioning works. I had a quick skim read of the paper, but I just wanted to.
Okay, so you should
get your view of it.
Yeah, it's the wisdom, I guess, 2019. But basically, we have this condition called R squared. We want to optimize R squared. So we do binary partition of the data so as to optimize R squared. And we continue doing this binary partitioning of the remaining classes until you no longer get improvement of R squared. And what R squared is measuring is the R squared measures is the difference in the outcomes between you take, the means within the groups and you have the mean across groups, and you're trying to optimize the difference between them.
So is this a cross between sort of random forests and clustering, essentially?
No.
I mean, the partitioning looks very similar to the splitting you would do on a piece of data in a random forest.
Actually,
the way you partition the space.
I should look, actually, if you look at Fennell, Lerman, and Zua, there's a EPGA data science paper we had last year, which actually talks in much more detail about, it's called S3D algorithm, that actually explains the nitty-gritty of the partition. And yes, actually, it's related to cart or decision trees, how it splits the data. Except that you're not at each level, you're not allowed to reuse the features again. So the feature can only appear once in your split. So it basically creates kind of a, but it explains the nitty-gritties of this partitioning. But yes, it is related to that. You're absolutely right.
Okay. My other question was, are these partitions done independently on an individual feature, or are they, so do you independently do this on X1, for example, and X2? Are they all considered independent?
Yes, in this particular implementation, they're just taking iterative, like you exhaustively, independently each feature is split. The S3D does disaggregation across all features. Like, this is another algorithm that mentioned S3D does that. So I should include the link to the S3D algorithm, which Fennell is the first author. It's EPGA data science paper. It has many more pretty pictures which are disaggregated according to multiple features.
Okay. Sorry, I'll ask one final question. Does this accurately identify the classes within the data, assuming there are such classes?
As far as we don't have any ground truth data knowing, what are the actual classes, but because it does give us this more interpretable conclusions, and we see then the same type of behavior across different systems, like whether we're looking at Facebook or Stack Overflow or League of Legends games also has the same kind of behavior, then that we have some confidence that these are correct trends that we're observing, finding.
Okay, great, thank you.
Mm-hmm.
Marcos has a question.
Hi, thanks for the presentation, it was quite nice. I want to know about this geometric solution that you talked at the end. I think it's a really cool idea. What I was thinking is, would that work with only if you have one protected feature? And if it's not the case, if you have more than protected features, I was wondering if you're gonna have conflicts, maybe you're gonna
Yeah. So this is a good question. No, but we can put multiple. The method itself can take multiple protected features, and then do this linear orthogonalization. To find space. The problem is if they're like conflicting, if they're like kind of mutually exclusive, then the null space will shrink to nothing. So there's nothing to project into it. That could be the limiting factor.
Mm-hmm.
If you take too many features and those features basically explain everything about the data, then you won't have this null space anymore. It'll be very small. So yeah. But you can take, the method is very general. But another thing about the method, it takes out linear correlations. So for example, you can still use, this is your income. It will take, and this is race, XP is race, and it will take up any dependence of race from the income. So you can actually use race-independent income within your models. And suppose the other one is like, education, it will take out, but if you take out any dependence between race and education, so you can use kind of linearly independent only. And in some points, if you use both actually education, race, and education as your protected features, there'll be nothing else left to explain. There won't be any null space because everything depends on those things.
Yeah,
I hope
that's cool because maybe you can show that there's some stuff that you can just use, right? Yeah, that's nice. Thanks a lot.
Mm-hmm.
Maybe you have time for the last question.
Mm-hmm.
So I want to make a question. So Kristina, do you think that the revealing or showing that this paradox or this hidden bias are helping or not help or harming science, in the sense like we have all this new wave, not new, but misinformation is all the way in the population not trusting on science. And then we have like very nice theory and plots in science applying, showing some trends that it's easy to understand, it's easy to accept. And then now we see a different study showing, oh, this is all wrong. See, that's completely the opposite. How this will
Are you saying that I'm undermining trust in science?
No. I want to say, how can we make this palatable for the population?
I know. In fact, data science, data analysis is really hard because it's so heterogeneous. And sometimes I do worry that people can find anything that they want, that they can find it in their data. So, it's all about constructing stories. Maybe Trump is right, maybe you can, if you talk about something and believe that's true, which many scientists often, will use their, use the data to validate their pet theories. Yeah, I do worry about that. But I think if we have good people telling stories and using data to support their beliefs, maybe it won't be so bad.
Yeah,
and I'm trying to also come up with examples where actually I changed my mind because of the data. Yeah, no, those are interesting philosophical questions actually, and that I've been actually also starting to think about this and struggle with it.
Okay, thank you so much, Kristina. Thank you, others, for joining us. And
thank you. It was fun. Thank you all
so much. It was very interesting.
Okay.
Thank you.
Yeah. Oh, somebody posted a link to APJ data science paper. Yeah, take a look. I like that paper. I should use more of the figures from that paper. All right. Thank you. Good luck for everyone.
And the recording will be online.
Okay, great. Thanks.
We'll share the link soon. Bye.
Okay, bye.